Hi guys, today I want to talk about equilibrium of forces. Equilibrium of forces. For forces to be in equilibrium, the sum of the forces acting on the object is zero. There is no resultant force. There is no net torque or no moment on the object either. No resultant force. The vector addition triangle will return back to its initial starting point when there is no resultant force. So we've got a force body diagram on the left, and then if I just add up the vectors, you can see we end up right back where we started with. That means that there's no resultant force. So free body diagram shows the forces acting on the body on the left, and then the vector addition triangle shows that there is no net force in this case. No resultant moment. Concurrent forces are forces whose line of action intersect at a single point. So the object on the left, the forces are all going through a single point, or the lines of action of the forces are all going through a single point. So this object will not rotate as the forces act at a single point. However, the object on the right, if we just draw where our lines of action are going through, you can actually see that for the three vectors, the three forces, the lines of action do not meet up at a single point, therefore there will be some kind of rotation. So this object will rotate as the forces are not concurrent. Ladder example, solved with concurrent forces in a vector diagram. So a uniform 6-meter ladder of weight 200 newtons leans against a wall at an angle of 60 degrees to the floor. What is the normal force acting against the wall? Okay, so it's 60 degrees, the ladder. Now, it's a uniform ladder, so the center of mass is going to be in the middle, and that's going to have a force of 200 newtons. That's the weight of the ladder. There's going to be a normal force acting on the ladder from the wall, and we don't know the value of that force, but we would like to find it out. And finally, there's going to be another force at the base of the ladder, and that's going to act not on the actual direction of the ladder, slightly up, and that, if you think about it, well, that's kind of opposing the frictional, is part of the frictional force stopping the ladder from moving or from sliding downwards, but also acting against the weight as well. So it's got this kind of diagonal direction. Now the ladder is not moving, so that means that our forces must be concurrent. So if we look at the lines of action, we can see that they all meet up. Okay, like this. Now, if we do this to scale, what we can do is we can draw a diagram and we can find this angle here, which, if we look at a vector diagram, is this angle here. So if we draw this to scale and we measure it, and we actually find that it's about 74 degrees, well, now we can draw our vector diagram to scale, even though we don't know the normal force, but we know this angle here, and we know that the angle between the normal force and the 200 newtons is also 90 degrees. So we can solve this distance here, which is around 57.7 newtons. Now, there is another way of solving this problem, and I actually think this is an easier method, and that's using the idea of moments. Now, exactly the same problem, but this time I'm going to show you how to solve with moments. So what we're going to do is we're going to take the moment about the base of the ladder. So that means we can ignore the force at the bottom, because remember, what is a moment? Well, it's a force times a distance, and there is a force there, but the distance to that point in space is zero. So if there's no distance, a force times a distance that's zero is zero. There is no moment produced by this force going up. So we only need to think about the normal force, or the moment produced by the normal force, and the moment produced by the 200 newtons. So firstly, let's think about the perpendicular distance from the line of action of our 200 newtons to the pivot point that we've chosen. And then we also need to think about what's the perpendicular distance from the line of action from the normal force to that pivot point as well. And we know these two moments, because our object is in equilibrium, these forces, the moments produced by these forces must be in equilibrium too. So the clockwise moment, okay, so this is 200 newtons times 3 meters, because why 3 meters? because the center of mass, where we're imagining this force of 200 newtons to be is halfway up our ladder. Okay, so the 3 meters times cos 60, that's the perpendicular distance in kind of like the orange dashed color, times by the 200 newtons, which is at 90 degrees to that distance to the pivot point, and we get 300 newton meters. So that's our clockwise moment. And then going anti-clockwise, well, the normal force, this time we're going to use the whole length of the ladder, which is 6 meters, and times by sine 60, because it's the opposite to the hypotenuse. And we know that that is equal to 300 newton meters because it's got a balance with the clockwise moment. So we just need to rearrange now, and then we find that our normal force is equal to 57.7 newtons. Okay guys, hope that was useful. Don't forget to like, comment and subscribe. Goodbye for now.